I am David. I'm the coordinator of the Maths Learning Centre, and I'm here to talk to you about statistics because, well, it's a part of your assessment this year, so it seems like a reasonable thing to do. Also, it seems to be a big part of the way medicine research progresses, and so the people who design your curriculum decided it would be a good idea for me to come. So I asked you guys to give me some statistics as it appears in some research articles, hopefully your critical appraisal ones. That's a nice place to find them. And of course my computer decides to turn off at that moment. Right, so these are some things that people have said, and there are a lot of different things, a lot of different words that are used around statistics. We've got the Mann-Whitney U-test, Bonferroni correction, Fisher's exact test, in multiple different spellings of Fisher as well. Only one of them is right. You'll see that the Mann-Whitney test sometimes is referred to with a U and sometimes without. Poisson regression, two-way ANOVA, Cohen's kappa, the student's t-test, all sorts of different things. Now, I can't possibly cover absolutely everything in 2 hours. So the plan is that I have in past years talked about a lot of these things, and I'll be breaking those videos up and they'll be available on the Maths Learning Centre website, and I'll send you a link to where it is when it's ready. And my plan is to actually have a little video on hopefully most of those things so that you can look up the specific one you need. Today is to give you enough information so that the things I say in those videos make sense. So that's the plan. All right. Good. So you'll see there's a heap of them. The most common things to appear are t-tests, ANOVA, and chi-squared tests, which most people have interpreted as x-squared, because how do you write a chi in a text box, at least in English anyway, and the Fisher's exact test. So I will talk about those ones today, so that you have an idea of the most common 6 tests that you will see. So that's the plan. So there will be several activities along the way, and there will be a bit of me talking and some presentations and that sort of thing. And you will have a chance, hopefully, to think about your actual research proposal / critical appraisal during this session, so that it actually leads towards something rather than just being generic information. And that's about it. And hopefully, by the time we get to the end of 2 hours, it'll all everything will make perfect sense, and the world will be a wonderful place. If not, and even if it is, I will be down here at this building on Thursday and Friday next week and Thursday and Friday the week after, and then next semester at some as yet undetermined times based on your timetables. And you can always come and visit me up at the North Terrace Maths Learning Centre if you want to talk about stuff. Okay, well that's where we are. So the first thing I want to do is talk about some stuff that will hopefully make everything make some sense. So I can't launch straight into what those statistical procedures are yet, because I need to give you some information about how statisticians think that will help make sense of everything. So that's what I'm going to do first. All right. So statistics helps to answer questions, that's what it's for, and it helps to answer questions in situations where things vary. The only reason statistics exists is because things do vary and we need to deal with variation. So statistics is based on a mathematical theory designed to understand and predict variation. That's why we have it. Because if everybody was always the same, you wouldn't need statistics. All right. So that's the big idea. It's all about variation. So the first piece of information is that statistics helps to answer questions, and questions in research are about concepts. Lots of questions are about a single concept, such as how much salt is there in an avocado. That's just about salt levels. It's just one idea. Or do kids finish all their homework? It's one idea, the percentage of homework that's finished. But most research questions are about the relationship between concepts. The simplest statistical procedures are designed to deal with one concept being related to another, but it can be more complicated than that. So, that's great. The second one might be something like Is smoking related to sudden infant death syndrome? For example, smoking in the mother. Is the thickness of a book related to whether it's a science fiction book? Those sorts of things. And that's not a medical one, but it's the one that popped into my head because I have to do this for everybody in the university, not just you guys. So, okay. And that's great, except that statistics does not work on concepts. Okay, your medical ideas work on concepts, but statistics only works on variables. And a variable to a statistician is anything that you would write down. It doesn't have to be a number, it's just a thing that you write down that would be different for different individuals. That's why it's called variable. So a concept becomes a variable when you measure it. And I draw concepts as nebulous thought clouds and variables as well-defined rectangles. So you can tell the difference between them in my drawings. Okay, and you might have something that has 3 variables relating to an outcome. So does your gender, what place you come from, and your age make a difference to whether you participate in volunteer work, for example? That's 3 things affecting one outcome. Okay, I should say that one of the hardest parts of science is figuring out how to measure your concept and turn it into a variable. For example, if you wanted to measure intelligence, how would you do that? And psychologists have spent a long time working on various tests that measure intelligence, but whether it's actually related to intelligence, the measure you get for, say, an IQ score is, well, in doubt. So it's really hard to tell how to measure some things. And that's not a statistics decision, that's a medicine decision. Think very carefully about how you want to measure stuff. I did help someone a while ago with an honours project which was about whether what people are wearing makes a difference to whether they're recognisable in video, and how do you measure recognisability? That's an interesting question. So, yeah. Okay. So here's the most important thing. So variables come in 2 types, 2 main types of variables. There is numerical variables, and when I draw them in pictures, I'll draw a box and I'll have the name of the variable at the top of the box and a symbol at the bottom to indicate what kind of variable it is. So on a numerical variable, I will draw a little scale like that to indicate the scale on which I'm measuring the numerical variable. And it's called numerical because it's a number. Okay? So in other places, in various places, you'll hear it called a quantitative variable. You'll hear it called a continuous variable. I put that in brackets for a reason, I'll come back to that. You'll hear it called an interval variable. You'll hear it called a scale variable. All of those mean that it's measured with numbers. So, well, we'll have some practice of this in a minute. So numerical variables are actual numbers, and you can tell they're numbers because how far apart 2 of the numbers are means something. If I gave you a little survey where you scored out of 7, whether you were satisfied with my teaching today, the difference between 5 and 6 is not necessarily the same as the difference between 6 and 7. And so it's not really a number. And that's what I mean by how far apart has meaning. Whereas my height, well, the difference between 167 and 168 is the same as the difference between 190 and 191. Differences are always the same meaning for real numbers. I'll come back to the continuous in a second. Categorical variables are categories. They tend to be words, and I'll draw them as boxes, which are the boxes that you put people in when you put them in categories. So you might put them in categories of eye colour, brown, blue, everything else, hazel with brown spots. You might put them in categories of what gender they say they are. You might put them in categories of where they were born. And some of these have lots of categories, some of them only have a couple, but they're categorical variables. You might also hear them called qualitative variables or nominal variables. Nominal means referring to names. Okay, this is a really, really important thing. The kind of variables that you write down about the individuals that you're studying make a huge difference to the kind of statistics you can do. At the most basic level, numbers, I can calculate an average, but what category people are in, I can just calculate percentages of who's in what category. And they're different calculations, and it's because it's different kinds of data. Right, I said I would talk about continuous. Many research articles will say, because we had continuous variables, blah, 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 What they mean by that is numerical, but technically continuous means that it's possible to get any number between any two you care to name. So with height, it's totally possible to get 190.5 and 190.75 and 190.753 technically. A discrete variable, if it's not continuous, a numerical variable might just be whole numbers, right, if you count how many things there are. So when a research article says continuous, they just mean numerical, and it doesn't necessarily mean that it's actually a continuous scale. It might be that it can only be 1, 2, 3, and 4. Okay. I have to say that to appease any statistician who watches this video at some point in the future. So there you go. I'm going to call them numerical and categorical, and what you are going to do is have some practice at choosing which is which, because this is really, really, really important. So what I want you to do is on your device, could you please go to student.desmos.com and type in this code. If you don't have a device or don't care to do this, then, well, it'll work perfectly fine if you're with someone next to you. And in fact, I would encourage you to talk together when you do this activity. Oh, look, there's some people. Okay, so it looks something like this. There's a whole lot of variables, and I want you to sort them into numerical and categorical, and I'll just put my mic down. Whether or not, so if I might do this, and it'll group them together like that. So you can drag them and put them on top of each other. You can pull them apart too. Please do talk to each other. Now, these are you, but I've changed your names, so do you want to see your own names? Yes. So everyone's doing some sorting. I will stop you in a minute and we'll see whether you agree with my sorting. Okay. I've just paused it. Okay. This is Gotthold Eisenstein's. I don't know who that is. It's one of you. You might be able to recognise it if it's you. And you may or may not agree with it. So I think what I might do is I might ask you what you think based on this. So a person's weight. Do you think that's numerical or categorical?
Numerical.
Beautiful. What country someone was born in? What do you think? Sweet. Whether skin is hairy or smooth? Mm-hmm. The number of days between heart surgery and starting exercise again? Sweet. How often a person takes a multivitamin? Oh, not everyone's quite as sure about that. Someone who said numerical, tell me why. Yep. Okay, so once a day, twice a day, once a week, and someone else said they're categories. Okay, well if it was all in the same time frame, then you could see it as a number. So if you asked people how often you take a multivitamin and you asked them actually, how many multivitamins would you say you take in a week, then that would be a number. And if you asked how often do you take a multivitamin and you put once a day, once a week or whatever, they're certainly in an order, but they're not really numbers because the difference between one and the other isn't the same. So it's probably most likely that this is a category. It depends on how you ask, which is one of the points I wanted to make. That if you ask a question in a certain way, you will get categorical and numerical results. Even if what you meant was numerical, it might come out as a category. All right, cool. So what I want you to do, I'm going to unpause it, is think of at least 2 variables in your research proposals, or just whatever variables you can think of, and write down what kind they are. So here's an example. You might, just in 2 lines maybe, whether the meal had chili, categorical, and the temperature, numerical. I'll be coming back to that example. So write some of them down. And you should be able to see what 3 other people have said when you do so. Sweet. I like this. Whether the child was born by vaginal delivery or C-section, that's definitely a category. Well done. Time from birth that the sample was taken, numerical. Excellent. Thank you, Gotthold. In fact, I recognise some of those, so Gotthold filled out the survey too. Well done. Whether they have a history of depression, categorical, number of children that the mother has, that's a numerical, well done. All right, you've all got this down pat, you're doing extremely well. This is the most important thing that you can learn to do to make sense of choosing what statistics goes with what. Excellent. I'm going to move on. I'm going to leave that open in case you want to play with it. Okay. All right. Yes?
Sorry, the variable like dosage be numerical? Like
dosage? How are you writing it down?
like grams.
So grams? If it's a number of grams, then numerical. But if you have, one dosage here and another dosage here, you could treat it as a category if you wanted. You had 2 groups with 2 different dosages. But if it was an actual number, you could try to use it as a number. Usually if you need at least, more than 2 possibilities for it really to behave like a number does in the formula. That's an excellent question. Well done. Okay. Right. So the next thing to know about how statisticians think is that to a statistician the word subject means whatever it is that is producing variables today. So and it's an experimentation sort of thing. The subject is whatever you're doing your experiments or study on. So there's not really such things as bananas and people in petri dishes to a statistician. There are just sources of variables. Okay, so we have a banana here, and I've written down its age, its weight, what variety of banana it is, and how much potassium it contained. We have some people. I've done an experiment where I've given them a meal with chili and at some other time a meal without chili, and I've measured their temperature after both meals to hopefully see if chili makes a difference. And I've got a petri dish, and I put a culture medium in it, and I've treated it, maybe with nothing or with some sort of antibacterial thing, and I've measured how many bacteria colonies there are on day 1 and day 2 and day 3, and they are categorical and numerical as they're shown. So subject to sources of variables, and there may be sources of hundreds of variables. If you're measuring genetic data, there'd be a whole lot of stuff going on. Also, variables can be used to calculate new variables. So the people with their 2 different temperatures, I could subtract them and calculate the temperature difference, which is also a numerical variable. And just because I calculate it from the data doesn't mean it's not a variable. It still belongs to that person. And from the number of colonies on day 1, day 2 and day 3, I could do some sort of thing and calculate a growth rate So just because a variable wasn't measured directly doesn't mean it doesn't count as a variable. Anything that you would write down about your subjects that is possibly different for different ones counts as a variable. Right. So you know how I said I had to appease the statistician who might watch it? This is the second thing I do to appease the statistician. When you actually do research, so this may not happen to any of you for a while, but when you actually do research and you collect data, the information about each subject goes in a row in your data set. So maybe it's in a Microsoft Excel spreadsheet or something, and I've got person number 1. This is a slightly different experiment. I've given each person one meal with chili or without and measured their temperature after that meal, but not everyone's had both. So person number 1 has a gender and an age and whether they had chili or not and a temperature, and I've recorded that in row number 1 because person number 1 has a row of their own, and person number 2 has row number 2, and person number 3 has row number 3, and all the genders are lined up in a column, and all the ages are lined up in a column, and all the chilies are lined up in a column, and all the temperatures are lined up in a column. That's how you put data into a computer. When I have asked statisticians, I say, oh, I'm doing a statistics lecture. What should I tell them? This is what they ask me to tell you. This is, if you can do this, then any statistician will be able to help you deal with your data. If you arrange it in any other way, it's going to be harder. Now, the computer says, please make it consistent. If you're going to have gender, don't put capital M and small m, and the word male, and the word male with a capital M, and the word male with a space after it. The computer will think they're all different, so make sure that you are consistent with the way that you enter your data if you're collecting data. All right. So the second thing I want to say about how data might be arranged is that if you have repeated measurements of the same thing on the same subjects, you may have to rethink what your subjects are. So here's my experiment where I've got people and everybody's got a meal with chili and a meal without chili, and I've measured their temperatures, and here's the data that I've mentioned. Supposedly if I was going to do more research, I would have more of them, but maybe I ran out of friends who would allow me to give them meals and measure their temperature. But it's a pretend story. But that seems reasonable. So that's how the data looks. And I've dutifully put the 2 bits of information I've recorded about each person in a row. But the problem is the information I want to know about is whether chili makes a difference to temperature. And I don't have both of those things measured on each person. The temperature, sure, but it's been measured twice. And the chili doesn't count as a proper variable because it's not measured separately for each person. It's in the headings instead of as a variable of its own. And that's going to make my statistics really difficult. So what I'm going to do is I'm going to rethink my subjects as a person-meal combination. You see they're holding a plate there. That's their plate. And so if I have a person with a specific meal, that meal has a yes or no for chili, and that person at that time has a measurement for temperature. And I can rewrite my data like this, and each subject has 2 rows, once for when they didn't have chili and once for when they did have chili. And what this allows me to do is have a variable that actually measures chili and a variable that measures temperature, but then I actually need a third variable that says which person it is. So there you go. What this type of data down the bottom is called long data, and the type of data above is called wide data, in case you ever need to know. But philosophically, in order for me to have a proper variable for chili, I need to consider the person different if they have chili and not chili, and just keep track of which person it is. Okay, last 2 things about variables. I can record variables about a group as well. So I could write down all sorts of things about the temperature of these 10 people. Of each person separately, I could write down their temperatures, but I can also calculate things based on those 10 temperatures. Maybe it's not 10, 1, 2, 3, 4, 8 temperatures. And I could write the median of the temperatures, so that's the middle one with half above and half below. I could write down the mean, so add them all up and divide by how many there are. I could have the percentage of them that are above 37 degrees. I could do the interquartile range, which is a measure of how spread out things are. I could do the standard deviation, which is another measure of how spread out things are. I could do the maximum. These are all things I could record about this group. And now the whole group becomes a new subject. I have a group with a new subject. So you could record measurements of schools or universities or towns or hospitals, and they can group all of the information together and make new variables that belong to the group. Just so you know, in a statistics textbook, these would be called measures of centre, the mean and the median, and these would be called measures of spread. Okay. So I do want to say that even though the maximum temperature is one of the people, it wouldn't be the maximum temperature in a different group if that person was in a different group. And so that maximum temperature is still information that belongs to the entire group. It's just important to realise that. So if you want to draw graphs of data or that sort of thing, then you can create new data by putting the information about groups in rows. And so group 1 that all had yes for Chile, they have their own row, and group 2 that all have no for Chile, they have their own row. It's not necessary to do this usually when you're doing statistical procedures. They'll calculate these things themselves. But you may want to talk about the groups rather than the individuals, in which case you're going to have to do this, and they call this aggregate data. So if you ever fill out a survey and they say in the consent form, only aggregate data will be used, that means that they're just going to use data about the groups rather than individuals. All right, there you go. These are some things to think about statistics. The most important ones are actually the type of variables. So keep that one in mind. Right, so now let's talk about choosing statistics. Now this isn't just for your research proposal, it also applies to your critical appraisal. If you can know how to choose statistics, then you can tell whether people have made the right choice when you've seen it. And you can also, if you know how to choose statistics, you can guess what statistics people used from the scant information they give you in their research paper. All right. So as I said, statistics helps to answer questions in situations where things vary, and it's based on mathematical theory designed to understand and predict variation. And different types of variation require different mathematical theory, which is why you have all these different statistical procedures. Okay, so there are two sides to choosing the right statistics. The first side is to know your question, and the other side is to know your data, because it's using questions to answer data. And there are 4 main purposes of statistical procedures. There are others, but these are the main ones. 4 main purposes for a statistical procedure, and they are to decide, to describe, to estimate, and to predict or explain. The first one I want to talk about is this. So the first purpose of a statistical procedure that you might see very often in research is to decide. And it's to decide the answer to a yes or no question. That's the simplest kind of question you can possibly ask, is a yes or no question. And statisticians have designed hypothesis tests, or if you like, p-values, which is what comes out of a hypothesis test, in order to answer yes or no questions. Every p-value that you read anywhere is helping to answer a yes or no question. So for example, I might say, is the median number of chapters in a novel 20? Yes or no. Is your body temperature higher after a meal if it has chili in it? Yes or no. Does getting more sleep affect a student's grades? Yes or no. Are women more likely to participate in volunteer work than men? Yes or no. They're all yes or no questions. All right. And that's what a p-value is for. And we'll come back to that in a minute to talk about that. The next one is to estimate. So you might want to estimate something. And so if you have a what's this number question, so what is the, well, here we go. What is the median number of chapters in a novel? How much higher is your body temperature after a meal with chili compared to one without? On average, how much of an effect does 30 minutes more sleep have on a student's grades? How much more or less likely is a woman to participate in volunteer work than a man? They are all questions about numbers. And when a statistician asks a question about a number, they answer it with a confidence interval. Confidence intervals are designed to answer what's this number questions. I'll talk more about the details of how that works soon. So, just let me go back. Those two that we just talked about, the estimate and the decide, I put them on the same level in my picture here because they use the same kind of data. They're sort of two sides of the same coin, or being as there are so many of us, the same side of two coins. Oh, no one's seen Rosencrantz and Guildenstern are Dead? It's a great play, you should see it. Sorry. I can't help but quote things if it pops into my head, so it might happen again. It's much more likely to be My Little Pony because I have daughters. Also My Little Pony is pretty cool. We estimate, right, cool. These use the same data and they answer two questions that are similar So one of them's about a number and the other one's just a yes or no question, but they're in the same situation. So they're really specific questions, the yes or no question and the what's this number question. They're really specific, and statistics is not particularly good at answering vague questions. And this is statistics' attempt to answer vague questions, just to describe what's going on. Your question is, what's going on? I don't know what's going on. What's going on? So how many chapters do novels have generally? What possibilities are there for body temperature? What sorts of things might be related to whether a person does volunteer work? They're really vague questions. And statistics is not particularly good at answering vague questions, but it can help. And we use what's called descriptive statistics, which is graphs, charts, that sort of thing, and the basic numbers like percentages and means. That's descriptive statistics. And you calculate it for your data and you go, ooh, that's interesting, and that's basically it. Okay? So, and you move forward from that to do real statistics. But often this is the first step. You'll take data, you'll do this and then say, well, what is this number? What is the average? And then you've got a what's this number question and you do a confidence interval. And finally, the most common, it's not the most common statistical procedure, but it's the most common purpose of research, is to predict or explain. I mean, the whole point of statistics is to be able to deal with variation and to say, well, what would happen if this? What would happen if I gave them this drug compared to this drug? I wanted to predict that so that when I can tell whether it's useful to use this drug or not. So that's what the predict or explain, but it might be, predict is about the future, explain might be, well, why do these people have lung cancer? And then I look at the past to try and explain the present. So they're really the same thing. And in a statistician's mind, when you're predicting or explaining, what you're doing is asking, what's the formula? There must be some sort of fabulous formula that I can put all the information in and it will spit out the prediction. That's what they're thinking. So how can I explain a person's body temperature after a meal using the temperature before and the chili content of the meal? I've got these two bits of information, the chili content of the meal and the temperature before, and I have some sort of formula that spits out what I expect their body temperature to be afterwards. How can I calculate a student's grade based on their number of hours of sleep during semester? It might not be a particularly accurate prediction, but on average it might be okay. And how can I use a person's gender, age, income and religion to predict their chances of participating in volunteer work? Okay, so you'll note that they don't have to be numbers in the formula. So in that third question, none of those things are numerical variables. They're all categorical variables, and it is still possible to create a formula to predict that probability, which is a number. So when a statistician does this, they call it modelling. Other people use other meanings of the word modelling, but statisticians use that. And the formula itself is what they call the model. So when a statistician says, I made this model, they mean I made a formula. Okay? So for a chemist, when they say I made a model, they mean, the thing with the balls and the sticks. When a physicist says I made a model, they mean some sort of physical relationship. When a statistician says they make a model, they mean they made a formula. And they do it by regression. So regression is the process by which statisticians use data to create formulas. It sounds like the English word for going backwards, but it's not. That's a historical quirk. The very first thing that these formulas were used for was predicting how much shorter children will be than their parents, which is why regression, because they're going backwards. So it was used for that first, and then suddenly that's what it's called forever. So that's what we've got. So regression is the process by which we model. Okay, sweet. So these are the four main types of question. You will notice that almost all research actually has a predict-or-explain purpose. But I said that p-values were answering yes or no questions. You'll notice that even though all research has a predict-or-explain purpose, most research articles are littered with p-values, which answer yes or no questions. And that's because in order to make a formula, I need to answer some yes or no questions, such as, is this variable related to the result? That's a yes or no question. And there's lots of those. Okay, sweet. All right, so what time is it? Let me just look at my list of what we're going to do and see if I can fit something in. Yes, it's time to get up and move around. So I need about 30 of you to come down here, please. What I actually have, let me just do this. on them. Could you come down and take a card and stand there, and once the cards are all full, then we know we've got enough people. Just one. You can look at it.
Well, I don't want to yell on it.
Haley.
The rest of you who aren't involved in this can just have fun watching these people.
Let's go that one.
I really should have got you to go on this side, but we'll deal with that in a second. Looks like we need about 8 more people. Okay, those of you who are here, have a look at your pictures. You might notice that these people have a name, they have a gender, they have weight and height, they have a vehicle that they drive. Some of them are smiling and some of them are frowning. Some of them have hats. Okay. Those of you already there, could you arrange yourselves in order of the height of your card, with the shortest people that way and the tallest people that way?
166. 166.
Yeah, 176. You'll be tall. Come down this end.
I'm 182.
179.
Go in front of the board.
171, I'm still short.
171, 172. 172. Darcy, what are you? You have to pick it.
Well done. Could you put up your hand if you wear a hat?
As your character?
Your character wears a hat. Okay, so tell me, those in the audience, does there seem to be a relationship between hat wearing and height?
No, surely not.
Someone commit. No? Why not?
It looks the same.
Okay, cool. So could you put up your hand if your card is female? Does there seem to be a relationship between gender and height? Right. This is descriptive statistics. We just arrange things, draw graphs, and go, this is what seems to be going on. Thank you, that was fun. Put your card back and sit down.
What about the video?
You wouldn't want to wait though.
I will have to remind myself to put the data, if you want the data, I'll put it on the website and you can investigate it if you want. It is made up data.
Thanks.
Okay. Describe. Okay, now that thing that we just drew there is not a traditional graph. Normally a traditional graph you'd have a scale of height and you'd line people up according to it, but this was the best thing I could do with getting people to move around. Though I can do those other graphs, I just need more space, that's all. Oh, crap. I'm glad you're impressed with my password. Okay. So, the second kind is to decide, which is the most common kind of statistics. So let's talk about that a bit more. So, hypothesis tests are designed to answer yes or no questions. Now this is some technical details. I'm not going to test you on it or anything. One of the answers, yes or no, is the null hypothesis. Okay, so it's usually the no answer, but it doesn't have to be. It's whichever answer that corresponds to something matching a specific simple situation, usually an effect of something not existing. So if we had chili and body temperature, the null hypothesis would be that chili doesn't make a difference to body temperature. That's the simplest thing that could possibly happen. The easiest thing to describe would be that it doesn't do anything. That's the null hypothesis. Okay, because there's lots of ways that it could make a difference. You know, lots of differences that it could make, but no difference is the simplest. Whereas if I said, do the majority of children complete all their homework, well, probably 50% would be the most thing with the least amount of information. Okay, and so you would run with that. So the p-value can be thought of a measure of how consistent your data is with the null hypothesis. So a lower p-value is stronger evidence that the effect isn't, well, zero. Like there isn't blah, blah, blah. It's all backwards, right? It's a proof by contradiction. You say, well, if there wasn't a difference, how consistent is my data with that there isn't a difference? So lower p-values tend to give strong evidence, and higher p-values tend to give you no evidence. So the classical places to cut it off is at 0.05, and under that you consider that to be strong evidence. So if I was doing my chili experiment and I got a 0.05, that would be strong evidence that there is a difference, because remember the p-value goes with nothing happening. So a higher number would be I believe nothing, and a lower number means I believe something. Okay, right? And most people call this 0.05 the significance level. You can pick a different number to go there if you want, but because Fisher, when he first did hypothesis tests, used 0.05, that's what everybody does. But you could pick a different level, and it's extremely common in research that has a lot of hypothesis tests for people to change that level so that it's harder for them to find results accidentally. Okay, so that's that. So what I wanted to do was to go and have a look at some of the p-value stuff that you found, not that one, in your papers. Cool. So I'm going to read some of them out. In both study groups, the most dominant bacteria for the first 6 months of life were the furniture phylum, caesarean section 78.96%, vaginal delivery 48.07%, P is 0.005. Okay, so that's great. That bit in the brackets there, what yes or no question is that asking? You'll notice it's quite hard to tell. It must be asking a yes or no question because there's a p-value. Yep. So is the furniture phylum the most dominant bacteria? It would seem to be asking that. It is a bit confusing because it's mentioned... Yeah, you're right. This is hard to tell. I should have picked a different one first. I think it's that p-value is actually comparing whether it's how common it is in caesarean section versus vaginal delivery. It's saying, does the delivery method make a difference to how common furniture phylum is? And the p-value is 0.005, so we conclude that yes, it does make a difference, because a high p-value would go with no difference and a low p-value would go with difference. Well, let's look at this next one, not that one. Yeah, I like this sentence here. After treatment, the changes in the environmental QOL, I suppose that's quality of life, was not different between the two groups significantly. So what's the yes or no question? So does treatment affect quality of life? And the answer is no, it doesn't. And you'll see that that goes with a high p-value, because low p-values tend to go with differences and high p-values tend to go with similarities. It's not always true, but I mean it's differences from nothing happening. Yes? I'm going to come closer, just a second. There's a big... Yes, I'm going to repeat what you said. You can tell me if I said it right. So in this one, was the null hypothesis was that the treatment doesn't make a difference to quality of life, and because they've got a high P value, they've accepted that null hypothesis. Yes, that's what's going on. Whereas this one, so the physical QOL was increased after treatment, and this is the p-value that goes with that. And so that's saying, was physical QOL different based on the treatment? And the null hypothesis is that it's not different, and so a low p-value says that it is different. So we reject that. And this one goes with psychological, and this one goes with social. So you see this one's getting pretty close to the borderline of 0.05. Not that it really matters. This one doesn't make any sense to me because this says that postural stability decreased more in the laparoscopy group than the robotic group, and then the P is 0.29. It doesn't make any sense to me because saying that there is a difference should go with a low p-value. So either this is typed wrong or they are wrong about their interpretation of the p-value. So, okay. Sorry? Trend. Yes, that's what a lot of people say. So a lot of people in that 0.05 to 0.10 category, most people say it's a trend. Anything above 20% is probably just not, just, yeah, don't kid yourself. So I like this one. So SBP and DBP decreased after meal ingestion. And so look, they've given you two different numbers and then a p-value. So my yes or no question is, does SBP change after meal ingestion? Does meal make a difference to SBP? And the p-value is low, so the answer is yes, it does make a difference. All right. Good, good. I'm very glad that I'm using your actual critical appraisal things because that means it's more meaningful for you guys. Normally I just do random examples. We're going to come back to this as well to try and guess what the actual statistical procedure they used is as well. Okay. Oh look, P is less than 0.05 is considered significant. You'll see that in almost every research article. That's what I mean by the significance level. And remember, the word significant is a statistical terminology. It doesn't mean important, it just means there. Okay, so a p-value of under 0.05 says the difference was observable. It doesn't necessarily mean it's meaningful. Okay. All right, there are a whole lot of other words that have been used here. Really hope that recording starts again in a minute. Should have done the moving around when in the gap. All right, we'll see. There might be a gap in the middle. Sucks to be everybody else who isn't here. Oh man. You see that as I get tireder, the narkier I'll get. All right, cool. That's p-values. Confidence intervals answer what's this number sorts of questions. So a statistician knows that because they have to deal with variation, they can't really just give one number as the answer. So if you have some data and you go, well, you go, I want to know what the average difference that chili makes to temperature, and in my data the average was, half a degree. That's probably extreme. Quarter of a degree. But you know that you're trying to estimate this for everybody who could possibly be in this study. It's all about everything that could possibly happen, and so you know that just that one number is probably not right. So you give a range of the possible things it could be. So a range of the possible numbers for what that number could be for all possible subjects. And what it does, it lists all of the values that mathematically seem consistent with the data. And so what you do is you get two numbers, and between those two numbers, those numbers appear consistent with the data, and outside those two numbers, those numbers appear not consistent with the data. And they normally say 95% confidence, and so there's different levels of confidence you can have in this. Often there is a specific number which corresponds to Lowercase what? No, but you're thinking how many curves there are. Did they write lowercase d is 1? No, it's always the same. I'm going to put it here. Just to help you along, I'm going to do a capital E. Okay, so one thing I'm saying that's really useful here is that you are all some people are starting to think about the shape of the letter, features of what the letter is, and what it does to this number. And that's exactly what you do in research, right? What features do these people have, and how does it predict what happens to them? I'm just going to check if I've got my answers right. Just a second. It doesn't matter. Let me do something that might help. No, not yet. So what do you think makes these different? Number of holes? Does that work for everything else? Does it distinguish between the E and the uppercase E and the lowercase e? Lowercase e certainly has more holes than uppercase e does, and its number is higher. All right, well, let me draw a diagram. So we may have no holes, 1 hole, 2 holes. And so far our numbers can be 0 and 1 and 2 so far. So let's see. P has 1 hole and its answer is 1. Little e has 1 hole and its answer is 2. Big P has 1 hole and its answer is 1. Little a has 1 hole and its answer is 2. Crap, you're right. I'm reading the wrong axis. Yep. Little d has 1 hole and its answer is 1. Big O has 1 hole and its answer is 2. Little b has 1 hole and its answer is 1. And big B has 2 holes and its answer is 2. F has 0 holes and its answer is 0. And I, little I, has 0 holes and its answer is 1.
So if it's a consonant, it's the number of holes.
Uh-huh.
It's the number of holes.
Right, so if it's a consonant, it's the number of holes, and if it's a vowel, it's the number of holes plus 1. Nice. Yay! There you go. Different languages, it works differently because they have different vowels. Okay, so I want to write this. The number is the vowelness plus the number of holes. So the number of holes is an actual number, but this, whether it's a vowel, you can say, well, 0 if it's a consonant and 1 if it's a vowel. That's how a lot of regression works. You pick a 0 or a 1 to be whatever the category is, and you can create a formula doing this. It might have been even easier to tell if I had done 2 times the vowel and added 2 if it was a vowel. Things would be much further apart. And there's another thing. The further apart thing, the bigger a difference it makes, the easier it's going to be to tell. Right, there we go. That's just a few very short little discussions about how these things work. Let's come back to my presentation. So we found a formula, and we managed to make it look like an actual formula, which is how statisticians do things. So they were just some illustrations of how those 4 different types of statistics behave. There are whole lectures on the details if you want to watch them. But the details aren't as important as being able to decide which one is which. So we know what kinds of questions we're asking and what kind of data they'll have. So, for example, if I wanted to, at the moment, use 2 different kinds of surgery, 2 different kinds of heart surgery, and then watch people for 10 years and record when they had their next heart attack, if at all, then there'd be a specific kind of statistics to go with that. Because I'm recording a number on each person, but also a category at the same time of whether something happened, and combining those together is the hardest of the statistical procedures, and it's called Cox proportional hazards regression. There you go. You know it's regression means that they're creating a formula. Cox is a person's name, and proportional hazards is the philosophy that's behind it. So there you go. So if you were going to decide that what you need is Cox proportional hazards regression or something else, you need to know your data. So first you need to know what variables are involved, and we've already talked about what kinds of variables there can be. So what variables are involved, you need to know what they all are and which ones are actually involved in the relationship that you're assessing at the moment. You need to know what kind of variable they are. So whether there's 2 numerical variables involved, or whether it's a categorical variable as an outcome or a numerical variable as an outcome, those will make a difference to the kind of statistics you're able to do. And then the next question is what distribution, which is a new word that I haven't mentioned so far. The word distribution means how things are spread out. You can talk about the distribution of a newspaper, which is where the newspaper goes, or the distribution of koalas in the Adelaide bush. To a statistician, the distribution is a description of all the things that could happen and how likely they are. So you pick a number and you go, well, what things could this number be and how likely they are? And you draw a little diagram where the height represents how likely it is. And so distributions can be approximately normal. Should be using this to save my voice, really. Distributions can be approximately normal, and that's what they call normal in statistics. It's sort of more likely in the middle and less likely at the edge. It looks a bit like a hat. And if you read the little prints, then it looks a little bit like an elephant inside a boa constrictor. See, told you, we're going to quote something sometimes. So it could be skewed. Skewed means that it's not symmetrical, it's longer on one side than the other. If you really care, the top one is right skewed and the bottom one is less skewed. Or it could be worse than skewed, it could be, that's called bimodal. None of these words are important, but you might want to know. And it sounds smart, you see, if you've got more words. It could be normal or it could be skewed, or worse than skewed. And if it's normal, most of the traditional statistical procedures are calculated based on the assumption that the data comes from a normal distribution. And the reason we need that is that the p-value is a probability. That's why it's called p. Now I said it was a measure of how consistent your data is with the null hypothesis, but it actually is a probability. And when you calculate it, the only way to calculate any probability is to know what all the options are and how likely they are. But it's not the probability for your original data, it's the probability for one of the calculations in your test. So you calculate what they call a test statistic. It's the probability of that thing happening. And so you have to know what the original data came from in order to be able to know the probability that comes out of your t-test or whatever test it is. And if you don't know, then you really can't use it. The magic of statistical theory says that if you've got enough data, it will be okay and you'll be fine anyway. So if you've got a large amount of data, you can just do the normal ones, and they're called parametric tests. And then if it's skewed, they'll use what they call non-parametric tests. Please don't ever use the word non-parametric data. Data isn't parametric or non-parametric. It's tests that are parametric and non-parametric. Parametric means referring to parameters, and the parameters they're referring to are the mean and standard deviation of that. So, a parameter is a number that describes something. So, cool. So if you ever see a phrase in a research article or anywhere that says we used a non-parametric test, then that's why, because they thought their data might not be normally distributed. And if you do a Likert scale, it is pronounced Likert, I looked it up, as opposed to Likert. So where you ask someone, you know, out of 7, do you strongly agree or strongly disagree to this? If you do a Likert scale, then the non-parametric test probably won't work. And you either have to do it as a number and assume it's normal, which it won't be, or treat it as categories. Because it's not really a number. So I'm just saying that now, because if at any point in the future you do things and you come to me, or your research supervisor says, can't we just do the non-parametric test because it's not normal? No, you can't do it on Likert scales. David said so. Okay, so that's it. I just needed to say it there. But in general, it really doesn't matter if you have a lot of data. If you have a lot of data, you can just do the traditional kinds of tests, which I will talk about very soon. And finally, you need to know what the categories tell you, okay, about how the data is set up. So in my chili experiment, I've mentioned 2 different ways of running the experiment. In the top one, I had every person have one meal, and it had chili or it didn't have chili, and that category split everybody into 2 separate groups, a whole group with chili and a whole group without chili. And so when I draw my diagrams, I'll draw something in specific so that that makes sense. However, I could have set up my thing where everybody has a meal with chili and a meal without chili, and then I could imagine that as sort of meal-person combinations with the chili and the temperature. So he's holding a plate there. That is a different thing to that person up there. So these are called the independent groups, and when I draw it in my diagrams in a minute, I'll draw the categorical variable, and I'll go 2 different people go into those 2 different categories. If that's how your data's set up, that the different people go in different categories, then that's an independent group situation. But it could be that the same person goes into both categories. And that's a repeated measure situation. I've measured the temperature for everybody twice, once with chili and once without. Some people call that a matched pairs situation, and the pairs they're referring to are the measurements of temperature. They're paired up because they belong to the same person. Okay, these are the bits of information you need to decide what statistics to do. And in order to make that clear, I am going to give you a handout. Later on when we go, feel free to come and get one if you want to give it to a person who isn't here. Okay, because I'm not that heartless. Nope, wrong one. So what I'm going to do is I'm going to illustrate how the different ways of recording variables and the different ways of arranging your data make a difference to what statistics can be done. I'm going to do it all with my pretend chili experiment. So they all have the same research question, which is, does the amount of chili in a meal make a difference to your body temperature? So this is my thought diagram, chili and temperature. And I'm going to have different decisions about how to record those as variables and different ways of setting up the data. Okay. So, let me... So, situation... situation A. One group has chili in their meal and one group does not, and I measure the temperature after the meal. So here's my person, and each person I've recorded chili as a yes or no and temperature as a number. I'm going to probably leave off drawing my diagrams in a minute, but we'll see how we go. So I have, does chili make a difference to temperature? And every person, different people are in different groups based on this chili thing here. That's the picture version of the of the data that I've got. So, there is a statistical procedure designed for precisely this situation, and there's a parametric one and a non-parametric one. So I may or may not tell you the non-parametric one, I'll decide that, but the statistics analysis to do here is called a t-test. There will be a word just here. It's called a t-test. All t-tests involve a numerical variable somewhere. So if you ever see a t-test of any kind, there is always a numerical variable in the outcome. Okay, it's a t-test, and this is called by various names. Most people call it the two-sample t-test. Some people call it the independent samples t-test. Some people call it student's t-test, named after a student who wasn't the real name of the person who invented it. He used the name student because he wasn't allowed to publish his work because he works for Guinness, the beer company. So that's the two-sample t-test. It's specifically designed to answer the question of, is this categorical variable related to this numerical variable when each person, every different person is in different categories? Okay, the non-parametric version of that is called the Mann-Whitney U-test, named after Mann and Whitney, who independently invented it in the same year without knowing about it. So, okay. So, what I mean about those two, they're designed to do the same job, but this one works under the assumption that your data is from a normal distribution and this one doesn't. Okay, that's situation A. Yep. What's that? So, the two-sample t-test is your standard one, based on normal distributions, and the Mann-Whitney U-test doesn't require that. The reason it doesn't require that, it doesn't actually use the actual numbers, it just uses the order they come in. So our story here, we're all lined up in order, but we didn't actually take into account what the numbers actually were. That would be a Mann-Whitney sort of situation. So, just so you know, I should say that if you've got a large amount of data, it doesn't really matter which one you do, so most people do the t-test. And the Mann-Whitney t-test was invented in like the 1920s or 30s, and the Mann-Whitney U-test was invented in like 80s, 90s. So it's not less well known. It's less well known. So second one, each person has both a meal with chili and a meal without chili at different times. Measure their temperature after both meals. So I'm still interested in whether chili affects temperature. And chili is still a category, it's with or without. And temperature, I'm assuming, is still a number, we've measured it. But this time, everybody is in both of these categories. It's a repeated measures situation. So the statistics analysis to do is still a t-test because it's a numerical outcome. It's called the paired t-test. Because all of my measurements are paired up because they belong to the same people. Oh, I can't even remember what the non-parametric version of that is. I think it's the Wilcoxon rank sum test. I'd have to look that up, I'm sorry. If you do see a phrase Wilcoxon, it usually means it's a, yeah, that's what it is. Okay, it's the Wilcoxon test. Okay. Yes? All right. So I'm happy for you guys at the moment to ignore these two until you see them again. Okay, and just focus on, ignore the ones in brackets until you see them again, and just do these ones. Okay, so the difference between these two is that they both have a category, which I'm wondering if it makes a difference to a number, but in this one, different people are in different categories, and in this one, everybody's in both categories. That's the difference between them. All right. So let's look at this one now. One group has chili flakes, one group has chili sauce, and one group has no chili. And we measure their temperature after the meal. So, how is this similar or different to the ones that came before? Okay, I'm going to repeat that. You check if I've got it right. It's like situation A, except there's an extra category. Does everyone agree with that? Okay, so we have 3 categories and a number, and everybody's in a different one of these categories. Okay, sweet. I said t-tests go with numerical outcomes, which is true, except not now. The test that goes with this is called analysis of variance. Which is also called analysis of variance, ANOVA. Why they don't call it AOV? Who knows? You may hear it pronounced ANOVA as well, depending on where you put the emphasis. Okay.
That one doesn't matter how many categories there are.
No, that's a good question. With ANOVA, it doesn't matter how many categories there are. You can have as many as you like. The more categories there are, the less likely it is to tell that there's a difference. Yes? Can you use ANOVA for 2 groups? Yes, you can, but everyone will think you're weird. Okay, so statistically, you can totally use ANOVA for 2 groups, and it will work fine. But people go, why are you using ANOVA for 2 groups? T-test is what 2 groups is for, because the t-test was a, yeah. It totally works. Did you have a question? Okay, yeah. So yes, you can use ANOVA for 2 groups. No one sat down and said, here are all the situations, let's make statistics for all of them and name them according to some useful naming system. It's just sort of all been made up over time. And this whole categorization that I'm doing here, well, I made this up myself. I don't know if other people organize it this way. So, okay. So, you may be asking, well, what if we had this, but everybody was in, but this situation, the same number of categories, but it was this one where everybody's in all 3 categories? That's called repeated measures ANOVA. And it's really hard. Like, it's really hard to do, it's really hard to tell what the hell is going on. I should say that when you do ANOVA, it just answers the overall question of does this category make a difference to this result? It doesn't say which category is different to which. And so what most people do is they follow up their ANOVA with a whole lot of t-tests where they just look at 2 categories at a time. Okay. All right. Here's my next situation. Groups are given, I really should have done that in milligrams, I'm sorry, I'm going to kill my participants, but groups are given 0 grams and 0.5 grams and 1 gram and 1.5 grams of chili powder in their meals. They're all dead, except the 0 grams. I measure the temperature after the meal. So how is this different to the one that came before? I can hear people saying, say it loud. Sorry? Okay, so I've heard two things. I've heard someone say there's 4 categories. I could totally do it as 4 categories, which would make it still an over. But because each category is actually an actual number, you know, and half a gram is certainly, the difference between 0 and half a gram is totally the same as the difference between half a gram and 1 gram. They're actual numbers. I can treat that variable as a number. Every person has chili recorded as a number and temperature also recorded as a number. There are times when I draw both because I feel the need to think about the individual subjects. So this question of repeated measures generally only counts if there's a category involved. I don't worry about that. Everyone has one measurement of chili and one measurement of temperature. And now I'm going to see whether chili makes a difference to temperature. Now, I said that regression was designed to answer what's the formula questions. Yes?
Sorry, I was just going to ask, so you still have to categorize the four different groups of people with different initial temperatures, different final temperatures. I mean, that's probably something about how I should run my data. I should probably not just do temperature, but the temperature difference for everybody. If I put people in those groups randomly, it should be okay. Because then because I did it randomly, they'll all have roughly the same initial temperature. And the philosophy is, well, each person is themselves, and I'm seeing what the relationship is between this and that for every person separately. It would be really cool if everybody had multiple different measurements of thing, and then it would be mixed effects regression, but we won't get into that. So I would do regression for this of some kind. There are lots of different kinds of regression, and you normally put a word in this position to indicate what kind of regression it is. So it might be linear regression, or logistic regression, or negative binomial regression, or whatever. Traditionally, the most simple one is called linear regression. Linear is referring to the kind of formula I'm making. So I said that regression was designed to answer what's this formula questions. And that's what it will do. It will create a formula that if you put the amount of chili in it, will predict how much the temperature is going to be. But along the way, in order to create that formula, I'm going to have to ask some yes or no questions. And if I ask the computer to do the regression, it will spit out all these p-values to go with it. And one of those p-values will belong to this question of, is there a difference? So technically, inside the linear regression, there's a t-test inside there. But most people won't talk about it at all. Okay. I should say as well that some people just use correlation, they call it. And they'll just say they did correlation test, but technically what they actually did is a regression. The computer didn't tell them that's what they did. So just for the purposes of today, these are the ones that are the most common. Okay. So when I put this slash here, they're the same thing, really, if I'm looking for the p-value anyway. All right. Sweet. So far we've had category affecting number in 2 different data situations. Category affecting number with a different amount of categories. Number affecting number. Well, let's go through our next one. One group has chili in their meal and one doesn't, and each person is asked if they feel hot or not. I'm not going to measure their temperature, I'm just going to ask them if they feel hot. So now temperature is a category, whether they feel hot or whether they don't. and everybody's in a different... Ooh, it's telling me to go home. I'm a bit closer to the train station here than I am up at North Terrace, so... Okay. So this is the situation we're in. We've gone back to situation A, where there's two separate groups, but this time our outcome is measured as a category instead of as a number. And that's going to change dramatically how the statistics can be done, because it's all about variation, and I can tell that two people are different better if it's a number than if it's in a category. Because there's only two options for a category. There's only, like, they could either be the same or they could not be the same, as opposed to having a distance apart. So there is a statistical procedure for this, and it is called the chi-squared test. I should point out that the chi-squared test works on any number of categories. Please don't pronounce it chi, you'll just annoy everybody. Just so you know, the name of this letter in English is normally written CHI. So the chi-squared test, I don't have to worry about non-parametric versions because already these aren't numbers to begin with. So every person has words written down about them. I create the numbers from the percentages, but for each individual person there aren't any numbers anyway, so I can just run with that. I should also say that Fisher's exact test does the same job. Why do we have two different tests? Well, when Fisher invented Fisher's exact test, he was deciding if people could tell whether milk was added before or after the tea, when people were making tea. And he only had a small amount of data. And so he created this test to do that, which he did with a small amount of data. But the thing is, it's really hard to calculate by hand. So back in the 1920s, before computers, it was really hard. And so Pearson came along and went, hey, I've got this idea. I'm going to create this test, which uses a chi-squared value, and it's going to be easier to calculate by hand. And so I'm going to use that one instead. So nowadays, when we have computers, it is technically possible to do the Fisher's exact test on whatever you want. And so it's starting to be more and more common now. Even though, I mean, it still took people like 60 years after the invention of the computer to really get anywhere, but whatever. So they do the same job. Yes?
So if the chi-squared test is the older one, or the newer one, sorry?
They were invented like within like 5 years of each other. It's just that this one can be done by hand.
Okay.
So is one better than the other? Good question. They produce the same results as long as the sample size is big enough. So Fisher's exact test is exact. It always produces the correct p-value. But the chi-squared test doesn't produce the matching p-value unless there's at least 5 people in every box. So you need enough people, if it's a thing on people, but you need enough subjects for the chi-squared test to be accurate. And so if you look at some statistics teaching resources, it will say that the Fisher's exact test is designed for small data and the chi-squared test is designed for a large amount of data. These days, you can always do the Fisher's exact test if you want. Yeah, so if you ask a computer to do the chi-squared test, it will always do Fisher's exact test as well, just in case you wanted it. It will tell you. So the computer will say, here is chi-squared test, here's Fisher's exact test, star, chi-squared test not appropriate. Yeah. But basically, when you put everybody in boxes, you need at least 5 people in every box. So there's 4 boxes here. Chili, feel hot, chili, not feel hot, not chili, feel hot, not chili, not feel hot. There has to be at least 5 people in every box for the chi-squared test to work properly. That's not important for your research proposal or your critical appraisal. Okay, even in your research proposal, if you say chi-squared test, no one is going to bat an eyelid. Okay? And if someone says, shouldn't you use the Fisher's exact test? You go, oh yeah, and you put it in. Okay? There you go. don't worry about it too much. But what I wanted to tell you about Fisher's exact test is because it was mentioned so many times when people put in their statistics from their research articles. So you need to know what it does. And what it does is tell whether a category makes a difference to a category. Okay, so this is cool. We had a t-test here, and we turned it into the chi-squared test. We had to use a chi-squared test when we changed to a category. What about like this situation, but when that's a category? So everybody's got both a meal with chili and a meal without, and I asked them if they feel hot or not for both meals. It would make a lot of sense if this was called the paired chi-squared test. But it's not called the paired chi-squared test. It's called McNemar's test, after the dude who invented it. But it's essentially the paired chi-squared test. Okay, it's the same. The relationship between the t-test and the paired t-test is the same as the relationship between the chi-squared test and McNemar's test. These are the 6 most common situations you can be in. The only other thing is when you have multiple things affecting the outcome. If you have multiple things affecting the outcome instead of just one, then you always do some sort of regression. Because in the background, in the mathematics, all of these can be done with regression if you want. Regression is really flexible and you can do whatever you want. But people don't talk about it that way. So these are the ones you'll see the most commonly, and you'll investigate what's involved in your research and what's involved in the research in the paper, and you will decide between these. So what I've got is some practice here that we can practice on. So for the next 3 or 4 minutes, I want you to have a go at those ones and make some decisions of what statistics you think goes with them. They're all one of the 6 that I've said. So have some practice. Please talk to each other. If you don't want to talk, that's fine, but you are allowed to talk. You're going to assume everything is normal, so just go t-test or whatever. All right, I've heard some really good discussions here. There are several things people mentioned that I would like to say. If I forget, remind me. Okay, so the first thing that isn't here and I probably need to draw, and I just want to say again, if your original research question, none of these are in those examples that I gave there, but I just want to say this. Your original research question may be this, for example. But you may also want to say, just take into account that actually maybe age makes a difference to this as well, and maybe gender makes a difference to this as well, and so on. In which case, it's not a t-test anymore. It was a t-test here, but now there's more than one thing affecting the outcome, in which case you will do regression. And what regression is able to do is be able to figure out whether this effect is there compared to these ones. And so that's what they mean when they say adjusting for whatever. And the second thing I want to say is that even if it was this, it's a bad arrow. Crap, that's the same. Even if it was this, it would still be regression, but it would be a special kind of regression designed specifically for yes or no outcomes, which is called logistic regression. Just so you know. Okay. The second thing I wanted to say is there a place you can go to get more practice at this stuff? And the answer is yes. On the Maths Learning Centre's website, which I'll email you the link to at some point within the next week, I have all of the past exam questions I've written on this topic, which are all of the type research situation. Which of these 5 tests is it? And I also have the long version of this handout, which has about 6 more pages that you can practice, which has my answers on it as well. I just changed it today, so it's just going to take me a few days to make the changes. Yes, and you can always come and ask me. Yes? Yes, I'm going to talk about that one as well. I'm nearly there. Okay, so I had 2 questions about the actual things, so I'm going to go to both of them, and you can check your answers. So I'm going to start at number 3 here. Is your IQ lower when you're responding to emails continuously? And so each person, so email is yes or no, and IQ is a perfectly good number. It might not represent intelligence, but it's a number. It's a score on a test. And every person has this IQ measured in both of these situations. And so the paired t-test is designed specifically to answer that sort of question. What someone asked was, this question said, is the IQ lower? And all of the questions I've mentioned so far are, does emails make a difference to IQ, which doesn't really indicate whether it's higher or lower. All of these tests technically only measure whether things are different, and they don't measure whether they're higher or lower, but you can still make the decision because the t-test will tell you whether it's different, and then you'll look at the averages and say, oh, well, this one's higher and this one's lower. So you can still tell whether it's a higher or lower situation, even with the paired t-test. And then someone has asked me about number 10. Does a student's consumption of soft drink affect whether they are physically violent? Okay. Students surveyed to find the number of cans of soft drink they consume per week. Okay, so soft drink is a number. School records are used to determine which students have been involved in violence at school. So violence is yes or no. And you haven't been shown something that does that. Oh, interesting. Okay, so the thing is that these statistical tests do not take into account which order the causation happens in. So I can think, well, people are in only one of these categories, and so it's the two-sample t-test. Now, when I say that, I mean, if you just want to decide whether there is a relationship, you can use the two-sample t-test in that situation. If you want to decide how much of a difference an extra can of Coke makes to whether the chances of being violent or not, that's a different question entirely. That is a what's the formula question, or a how big is his number question, which means you should use some sort of regression. And because it's a yes or no outcome, it's logistic regression. Okay. That's telling me that I have only minutes to go. So I'm going to do the last thing that I was planning to mention, even though I could have gone through all the answers, and I'm sorry. I wanted to mention at least once sample size calculations. So this handout will be on the website, and there is a whole lecture on sample size calculations, well, maybe half an hour lecture.